me jump straight ahead and tell you what the main question of the work is. So what we were interested in is whether it is possible to speed up convex optimization, and by speed up I mean reduce the number of iterations. And the way you could try to do it, and really the only way you could try to do it given sequential lower bounds, is by using parallelization. Now, there is a reason to be optimistic about this problem, and it comes from submodular maximization, where this type of parallelization has proven to actually be useful, and submodular maximization is not too far from convex optimization, but as we will see, the situation is much different from convex optimization. So the basic problem we are considering here is just minimizing a convex function over a convex set. We are not able to look at all possible algorithms, so we restrict our attention to those algorithms that work in the local oracle model. This means that the algorithms can query an oracle. They query an oracle by providing a point from the feasible set, and the answers they get, based on which they construct the next point, are some local information about the function. So this can be gradient or a function value or any Taylor approximation. Here is a more formal definition if you're interested, but the whole point is just that you don't reveal anything that does not correspond to a particular point you're querying. In terms of algorithms that work in this model, it's most of the algorithms we tend to use. So it's not only first-order methods, but even things like cutting planes and ellipsoid. Methods that do not fall into this category are proximal methods. There are some lower bounds for these settings, but we do not consider those methods in this work. Let me now clarify what I mean by parallel. I certainly do not mean parallelizing one iteration. This is in general helpful, like parallelizing the computation of a gradient. What I do mean is querying many points in parallel to try to reduce the number of iterations. So what your iterations would look like, in every iteration, as shown on the right, you would choose some k points from the feasible sets. You would query the oracle and receive the local information about the function. And then in the next iteration, you just repeat the same thing, but now you can adapt to whatever you learned from the previous rounds of computation. So maybe you can query the points that are closer to the function minimizer. Since I'm talking about lower bounds, I need to tell you about the notion of complexity we are using here. So let A be some fixed algorithm. We also need to fix a problem class, and to fix a problem class, we fix a class of functions, so maybe all Lipschitz continuous functions or all smooth functions. And to talk about complexity, we need to specify how we are evaluating algorithms, and so this t will be the time an algorithm takes until it can query a point that is epsilon close to the minimizer in the function value. So the time it takes to land below that upper hyperplane. So the complexity of a fixed algorithm is its performance, its running time on the worst case instance from the class. So when you want to talk about complexity of a problem class, you look at the best algorithm in terms of its time, its complexity, and you can look at all the deterministic algorithms or all the randomized algorithms, and one very general way of looking at algorithms is in the high probability complexity model. So here you can look at all randomized algorithms, and you even allow them to only succeed with probability gamma. So this is the complexity model that we adopt here. It is stronger than the previous two complexity models. Okay. The results I will be showing here are for LP geometries. When I say LP geometry, I mean that all the distances are measured with respect to the p norm. When we work with the LP geometries, we fix the feasible set to be the unit p-ball, or at least to contain a unit p-ball. This is a standard setting for understanding the complexity of a certain class. Our lower bounds are actually robust to the enlargements of the feasible set, and they also apply to unconstrained optimization. So this is all without loss of generality. And All of these lower bounds easily also generalize to the spaces of matrices and Schatten P norms, which are LP norms of the matrix singular values. The main result is that it is essentially impossible to reduce the number of iterations of convex optimization in a high-dimensional regime, so dimension is poly 1 over epsilon, for any level of smoothness of the function, so non-smooth Lipschitz, weakly smooth, or smooth function, essentially any interesting geometry, LP and Schatten P spaces, with any polynomially bounded in the dimension number of queries per round. And now there is still the round impossible because not all the lower bounds I'll show you are tight, but they really leave very little to hope for. So here is a table summarizing the results. All the results except for the top left entry are for the high dimensional regime. So the first result for the L infinity is the one that is the loosest. In fact, this result only existed for the weaker worst case complexity model, and it's due to Nemirovsky since the 1990s. It has not been improved since then. It's not also improved by our work. But if you made an improvement on this result, you would get actually tight lower bounds for anything that's not tight in our results. Smooth P infinity case is essentially tight. P between 1 and 2, the only case that's not tight is for the smooth case. The exponent in epsilon is off by 1 over 10. So, but if you improve the L infinity bound, you would get the right exponent. The rest for P greater than 2, essentially any constant P is tight. I should mention that the case P equals 2 was obtained independently and prior to our work by the work of Woodward et al. And Balkansky and Singer. And the last thing I want to mention about this table, that except for P equals 2, this whole row of the table was not known even for the sequential case for the high probability complexity model. Okay. Now, I want to say a few quick words about the techniques. What we do is we prove a general lower bound. So we give a theorem that applies to arbitrary norm spaces and for any smoothness level of the objective. And what we require is that the feasible set contains the unit ball measured with respect to the norm that you fixed. So the way we get all these results for the LP geometries are just by applying this theorem for specific, by showing that we can satisfy the conditions of the theorem. Now, similar to what was also done previously in the literature, the arguments is based on the existence of special independent random vectors that are supported on the dual ball. And at a high level, these vectors represent the signature of your objective. You really need to learn them all to be able to construct a good solution. And the main argument is that you can only learn one vector per round of queries. What is really happening is that you're hiding these vectors in a higher dimensional space, and this is precisely where this high dimensional assumption comes into play. And as I already mentioned, so to apply this theorem, we give specific vectors, Z1 to Zm. I won't go into what they are, but you can maybe ask me at the poster. So in summary, in the high dimensional regime, for almost any interesting setting of convex optimization, you cannot improve the iteration complexity of convex optimization by using parallelization. Now, some open questions that we're interested in, one is, are there structured classes of problems on which you can actually gain from parallelization? And the second is the low dimensional regime different? It seems like this case may be easier. There is a paper by Bubek, Zhang, Li, and Sitford, and Aaron and Yintat are around, so maybe they can tell you more about it. I haven't had the chance to read it yet. If you want to ask me more about this paper, I will be at poster 177, and thank you very much for listening.
You said D has to be 1 over 1 epsilon, so what's the power of epsilon to get that?
it depends. It depends on the specific setting. You know, sometimes it will be like 1 over epsilon, I don't know, fourth. Sometimes it can be higher. Something is just 1 over epsilon squared. So it really depends.
What is it for p equals 2?
Oh, I don't remember. Yeah.
Okay, all right, thank you.
Yeah.
Let's then speak again. Okay, the next talk by Blake is on a paper that is a co-recipient of the Best Student Paper Award. So let's congratulate Blake and his co-authors. And it's on the complexity of making the